All right, so welcome back for part 2 of 8.5. This is, what is this? This is expected value. All right, so we made a bunch of probability distributions in the first part of this video, but the question was why, like as in who cares? All right, so here's where we're going to try to bring probability and who cares kind of together. All right, so let's make it real simple. All right, suppose you graduated from Glendale Community College and you have a job at the washing machine company. And the boss comes to you and says, how long should our warranty be? So they're putting out a new washing machine. How long should our warranty be? Because if the washing machine fails during the warranty period, the company loses money. And so as a company, I want to stand behind my product, but I also don't want to lose money. So what is the length of time that that warranty should extend to so that I can feel good about standing behind my product, but not lose too much money? And so if I think about this in terms of a probability distribution, our X and our P of X here would be the number of years or the number of the probability that the number of years, like 1, 2, 3, 4, and then down here would be the probability that the machine fails in those years. But maybe more than 1, 2, 3, 4, maybe we should think of this as how much money will it cost if it fails in year 1? And how much money will we have to pay if it fails in year 2? And how much money and how much money and how much money? So rather than looking at this as year 1, if we said, well, we're going to give them all their money back in year 1, so that'll cost us, just to keep things simple, $500. And then in year 2, we only give them back $300. And in year 3, we only give them back $100. And then in year 4 plus, we give them back nothing because our warranty is only for 3 years. So then how much will that cost us? And is 3 years enough? Is 3 years too much? Should I go to 4 years? Should I change these numbers? Those are the kinds of questions we're going to try to answer when we take a look at the expected value. All right, so mathematically, the expected value of a probability experiment is the average of the experiment if you were to run that experiment many times. Right? Imagine, if you will, that you have 2 dice. And you roll those 2 dice again and again and again and again and again. And then every time you roll the dice, you record the sum of the 2 dice. Right? What would be the average sum of the 2 dice? Because sometimes you're going to roll a 2, and sometimes you're going to roll a 5, and sometimes you're going to roll an 8, and sometimes you're going to roll a 10. But on average, what would you expect to roll? Right? That question can be answered by taking a look at the expected value of an experiment and what is the math that makes that work. Okay? This idea of expected value is the math behind every industry that runs on probability. Probably the biggest one that you're aware of is insurance. Because insurance is just gambling. You're making a bet, they're making a bet. When you buy car insurance, you're betting that you're going to get into a car accident. They're betting that you're not going to get into a car accident. Right? The reason I say you're betting that you are is the only way that gets paid is you get paid is if you get into an accident. And then they're betting that you're not because they want to keep your premiums and not pay out. All right, so let's take a look at the formula. The formula for random variable expected values says that if you have the random variables for an experiment and you know those, and you have the probabilities and you know those, then the expected value is just going to be the sum of the product of those probabilities. Okay. So that's going to be all of the possible outcomes, those are the X's, all of the probabilities, those are the P's, multiply the X's times the P's, and the X's times the P's, and the X's times the P's, and then add them all up. Okay? There is one exception to this rule, and that exception is that if your experiment happens to be binomial, you can just take n times p. Remember where n is the number of trials and p is the probability of success, and that works out. All right. Our first example, let's put some numbers into this. Find the expected value, find the average for rolling 2 dice and recording the sum of the dice. Now, I already know what the probability distribution looks like. The probability distribution looks like this. We just did it in the first part of this video. You could roll a 2, you could roll a 3, you could roll a 4, you could roll a 5, you could roll a 6, you could roll a 7, you could roll an 8, you could roll a 9, you could roll a 10, you could roll an 11, or you could roll a 12. And I remember that the probabilities were 1 out of 36, 2 out of 36, 3 out of 36, 4 out of 36, 5 out of 36, 6 out of 36, 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, and then 1 out of 36 on the end. So now our expected value, what we would expect to see if we ran this experiment again and again and again and again and again, is going to be all of those x's multiplied by their p's and then added up. So I'm going to take every single one of these x's, multiply it by its p. That is, I'm going to take 2 times 1/36 plus 3 times 2/36 plus 4 times 3/36 plus 5 excuse me, times 4/36 plus 6 times 5/36 plus 7 times 6/36 plus 8 times 5/36 plus 9 times 4/36 plus 10 times 3/36. Let's see if I can fit it in. Plus 11 times 2/36 plus 12 times 1/36. And add that all up. Sorry, I got kind of small there at the end. All right. And so let's go ahead and do that. I'm going to get an expected value then of, now you'll notice that all of the denominators are all going to be 36. So I'm just going to write this as one big giant fraction, where it's going to be something over 36. And the first one, it's going to be 2 times 1, and then 3 times 2, and 4 times 3, and da-da-da-da-da-da-da-da-da-da-da-da. So I'm going to get 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12. Okay? 2 times 1 is 6, 3 times 2 is 6. I'm sorry, 2 times 1 is 2, 3 times 2 is 6, 4 times 3 is 12, 5 times 4, 6 times 5, 7 times 6, 8 times 5, 9 times 4, 10 times 3, 11 times 2, and 12 times 1. And now I'm going to grab my calculator, and I'm going to say, what's 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30, 22, 30 plus 22 plus 12, and then divide that by 36, and I get a expected value, or an average of 7. So in the long run, if I sit there with my 2 dice and roll and record 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 and roll some more and record some more and then roll some more and record some more, the expected value is I'll roll a 7. The average value is 7. All right? So the expected value, my job is to find these things. I just found one. All right? Let's take a look at another example. Now, before I move on though, real quick, who cares? Who cares that that's 7? Well, dice, gambling, Vegas, there's a lot of money to be made if you can predict how the dice are going to land. if you know the probability of this or the probability of that, or what is most likely to occur. All right, next problem. Suppose the 5 apples in a barrel of 25 apples are rotten. The other 20 are good. Find the expected number of rotten apples in a sample of 3 apples. So I've got a barrel of apples. In that barrel, there are some good ones and there's some bad ones. Over here are the good ones. Over here are the bad ones. There are 20 good ones and there are 5 bad ones. I'm going to reach into there and I'm going to pick a sample of 3 apples. And so what's going to happen is I'm going to sometimes get good apples, sometimes get bad apples, and sometimes get a mix of them. And so what could happen? If I want to find the expected number of rotten apples, how many rotten apples could I pick? Well, I could get 0 or 1 or 2 or all 3 of them could be rotten apples. What's going to be the probabilities of these things? Well, what's the probability that I'll pick no rotten apples? So I'm going to do some scratch work over here on the side. The probability of no rotten apples means that out of the 25 choose 3 downstairs, I'm going to do 20 choose 3 upstairs. And so I'm going to need to do the math to figure out what that is. So let's see, I'm going to bring up my calculator. Let's see, 20 math NCR 3. That's 1,140 over, and let's see, I'm just going to do this. I'm going to cheat a little bit. Go back up there, and all I'm going to do is change that 0 to a 5. 2,300. And so then 1,140 divided by 2,300. Make that into a fraction for me. I get 57 out of $1.15. So this one's going to be 57 out of 115. All right, so now I'm going to find the probability that I will pick 1 bad apple. I know it's going to be 25 choose 3 downstairs. Upstairs is going to be 20 choose 2 times 5 choose 1. Okay. This is going to pick 2 good apples. This is going to pick 1 bad apple. Okay. And now I need to find out what that fraction is. See what that's equal to. So I'm going to come over here, clear. I'm going to do this one a little differently. 20 choose 2. So times 5 choose 1. Well, I know that 5 choose 1 is 5. And I know that this is 2,300. And that gives me 1946. All right. Now I'll do 2 bad apples. So the probability of 2 bad apples is going to be something over 25 choose 3. So it's going to be 20 choose 1 times 5 choose 2. Right? This is going to pick the good apple. This is going to pick the 2 bad apples. Right? So again, I'm going to make a fraction. I know downstairs is 2,300, so I'm just going to put that in. Upstairs is what? 20 choose 1 is 20 times 5 choose 2 is 10. I just happen to know that. You can check it if you don't believe me. And I get 2 out of 23. Whoop. So then this is going to be 2 out of 23. Last thing I have to do is I have to do the probability that all 3 will be bad apples. So I know it's going to be 2,300 downstairs. That's that 25 choose 3. But what's my numerator going to be? Let's see, it's going to be just 5 choose 3. Because I don't want to pick any from the good pile, so I just want to pick 3 from the bad pile. Let's see, 5 choose 3. So 5, math, NPR 3, I think that's 10. So it's going to be 10 out of 2,300. So 1 out of 230. So 1 out of 230. Now I'm brand new at this, so I'm not sure I really trust myself. So how am I going to check my work? Well, I'm going to check my work by doing this. These 4 numbers right here, if I've done everything correctly, those numbers should add up to 1. So 57 divided by 115 plus 19 divided by 46 plus 2 divided by 23 plus 1 divided by 230. Hey, what do you know? It adds up to 1. I must have done it correctly. Now I can go ahead and find that expected value. So the expected value, the E of our x, our expected value, is going to be each of these numbers oh man, I just realized something. You're going to love this. When we do our expected value, we multiply the x times the p, the x times the p, the x times the p, the x times the p. But since that one's a 0, did I even need to know what that is? It's just going to get multiplied by 0. I don't know. I guess it isn't the worst thing in the world. So I'm going to take 0 times 57 over 115 plus 1 times 19 over 46 plus 2 times 2 over 23 plus 3 times 1 over 230. I'm just going to chuck this mess in my calculator because that's I'm not going to try to do that by hand. So let's see, I've got 19 divided by 46 plus 4 divided by 23, the 2 times the 2 right here, 2 times 2 is 4, plus 3 divided by 230, that's the 3 times the 1, and I get 0.6. So my expected value is 0.6. But what on earth does that mean? Well, that tells me that if I were to reach into this barrel and pick out 3 apples again and again and again and again and again, each time going into a barrel with 25 or 20 are good and 5 are bad, 20 are good and 5 are bad, and 20 are good and 5 are bad, something would happen. And that something is that in the end, on average, I would see that many 0.6 bad apples per trial of the experiment. All right, let's see if we can bring this around and make it more applicable, no longer about apples or rolling dice. An insurance policy on an electronic device pays a benefit of $4,000 if the device fails during the first year. The amount of benefit decreases by $1,000 each year until it reaches 0. If the device has not failed by the beginning of any year, the probability of failure during that year is 0.4. What is the expected benefit under this policy? All right, so I've got a probability distribution here where I've got x's and I'm going to have p of x's, and those x's and p of x's are going to represent the money that we have to pay out. Right? So if this thing fails in year 1, I've got to pay them $4,000. And if it fails in year 2, I've got to pay them $3,000. And if it fails in year 3, I've got to pay them $2,000. If it fails in year 4, then I've got to pay them $1,000. And if it fails in year 5 or more, I pay them nothing. Right. Now I need some probabilities. Let's see, 0.4. So if it doesn't fail, the probability it fails in that year is 40%. Now I know what you're thinking. Then this is 0.4, and this is 0.4, and this is 0.4, and then this, but that adds up to way more than 1. So they're not all 0.4. In fact, if you think of this in terms of a tree diagram, it either fails or it doesn't fail. And in the first year, that's going to be 0.4, and this will be 0.6. Fails or doesn't fail. This is 0.4. And so to get to here, I need to have one not fail and one fail. So that's going to be 0.6 times 0.4, or 0.6 times 0.4, which is 0.24. To get to year 3, I need to have 2 doesn't fail and 1 fail. So that's going to be a 0.6 times a 0.6 times a 0.4, which makes this oh, I don't want the highlighter, 0.144. To get to year 4, I need another doesn't fail. So another 0.6 and another 0.6 and then a 0.4. So 0.6 times 0.6 times 0.6 times 0.4. So this is going to be 0.0864. And then what's going to be the probability for the rest of them? Well, the rule for probability says that all of these must add up to 1. So then to find that missing piece, could I just take 1 minus the known pieces? And so to find that missing piece, and boy, that got weirdly small, I'm going to take 1 minus 0.4 minus 0.24 minus 0.144 minus 0.0864, and I get 0.1296. So 0.1296. So now that I've got my probability distribution all drawn, now I can take a look at finding the, why does it keep doing that? That's so weird. Now I can take a look at finding the expected value. Right? Remember, the expected value is going to be these two multiplied together, those two multiplied, those two multiplied, those two multiplied. So it's going to be 4,000 times 0.4 plus 3,000 times 0.24 plus 2,000 times 0.144 plus 1,000 times 0.0864 plus, I can't see that last column, but I know that's a 0, so 0 times anything is 0, so I really don't care that I can't see it. And I see that I get 2,694.4. And so what does that mean? That my expected value is 2,694.4. Right? Well, that means that if I am the insurance salesman and on average my payout is this. So if I sell a bunch of policies, policies, then on average each policy will cost me $2,694.40 in claims. So for every policy I sell, on average, I'm going to pay out $2,694.40. Is that a bad thing? How much do these policies cost? Well, I know that I'm going to have to charge more than $2,700 per policy, otherwise I'm not going to make my money. I'll be in the red rather than being in the black. I'll pay out more than I'm bringing in. So this is an example of how this whole idea of probability and expected value and probability distributions kind of comes all together, right? So I want to sell insurance policies for new printers because companies buy new printers. So everyone's buying a new 3D printer. They want to buy an insurance policy, so if that thing breaks, they'll get paid. I want to sell them an insurance policy. I want to make money. So I need to know, on average, what these policies are going to cost me so that when I sell them, I sell it for more than what it's going to cost me. So I find out what I'm going to pay out if it fails in year 1, what I'm going to pay out in year 2, what I'm going to pay out in year 3, what I'm going to pay out in year 4. Then I find out what is the chance, the probability for it failing in all those situations. The expected value then, the average of this probability distribution, tells me that on average, if I sell enough of these policies, it's going to average out to about $2,700 that I'm paying out. So then I look at that and I go, well, okay, as long as I charge more than $2,700 each, I'll make money. Okay. Let's skip this one because I put it in here, but actually I really don't like it. And let's do this one, and we'll call it a day after that because we're at 25 minutes now. The other application of expected value is the idea of gambling, and that's where probability theory got its original start. Is people wanted to know how to gamble, and they wanted to know how to gamble correctly. All right, so let's take a look at a simple casino game, American Roulette. American Roulette has a wheel. There are 38 numbered slots on that wheel. The numbered slots are the numbers 0, 0, 0, 1, 2, 3, all the way up to 36, okay? So these two right here, these are green. There's a green double 0 and there's a green 0. And then the rest of them, the 1 through 36, those alternate back and forth, black and red, black and red, black and red, okay? All right, so suppose that I place a $1 bet on a single number, any of those numbers right there, and I win. Well, if I win, the casino will pay me $36. If I don't win, then I just lose my dollar, right? My job is to calculate the expected value of this game. All right, so the first thing I'm going to do is I'm going to create a probability distribution with x's and p of x's. Now, the nice thing about this is there are only two outcomes. There's the I won outcome and I lost outcome. Right? I know that if I lose my dollar. How much will I win if I win? Now, I know that you want to say 36, but technically it's 35. Because if I put $1 down and I win and they hand me 36 back, I really didn't win $36, I won 35. Right? What's the probability I'll win? Well, there's a 1 out of 38 chance that I'm going to win because there's 38 places for the ball to land in the roulette wheel. Only one of them's a winner for me because I bet on a single number. Right? There's 37 out of 38 ways for me to lose. And there's my probability distribution. Now I can find the expected value. So what is the expected value of this game? Well, the expected value is going to be 35 times 1/38 plus -1 times 37 38ths. Now that math isn't too bad to do in our heads. That's going to be 35 minus 37 over 38, which is -2 over 38, which is approximately -0.05 and change. Okay? If you really want to know what the number is, here it is. 2 divided by 38 is -5.2. So what does this tell me about Vegas? Well, this tells me that in Vegas, if I place a $1 bet, on average, I lose about 5 cents. Now, remember, this is the key word here. The expected value says that to make this happen, to make this be true, a single individual would have to go sit down at that roulette table and place a bet, $1 bet, $1 bet, $1 bet, $1 bet, $1 bet, $1 bet, again and again and again and again and all day long. That's not realistic. People don't play that way, but that's how Vegas plays. Vegas keeps track of the expected values for games. And this number right here that we just found, this 0.05, this is not unique to roulette. This is the average for most table games. Most table games in Vegas, if you calculate out the expected value, are about a negative 0.05, meaning that for every dollar you bet, you lose about a nickel. So if you placed a $2 bet, you'd lose about 10 cents on average. If you placed a $5 bet, you'd lose about 25 cents on average. Right? So for every dollar you're betting, you're losing about a nickel, because you lose, but then you win. But then you lose, but then you win. And then you lose, and then you win. And the way that it averages out is they're keeping a nickel every time you bet a dollar. A nickel doesn't sound like much, but if you had a big enough pile of nickels, you can run the lights of Vegas and you can make a lot of money. There are very few games in Vegas, if any, where the expected value isn't negative from the player's perspective. Now, if this was the casino's perspective, of course, this would be the negative number, this would be the positive number, and that would make this positive 0.05, because they'd be keeping 5 cents versus losing 5 cents. But we wrote this from the perspective of the player, not the casino. That's expected value. That's how it gets wrapped up. Okay? Anytime you're making a bet on something, anytime you're gambling, anytime you're selecting some sort of thing to happen or not happen and putting money on it or getting paid, whether it's an insurance, whether it's buying a lottery ticket, whether it's going to Vegas, okay? This is all about gambling. At its core, that's the math. And expected value tells you what to do. A fair game is when the expected value is 0. Negative expected value means it's in favor of the other people. A positive expected value would mean it's in favor of you. All right, that brings us to the end of section 8.5 and the end of chapter 8. So it's time for an exam. All right, have a great day.